In the last lectures, we have been discussing about this unimorph and bimorph concept, the usage of these unimorph and bimorph in different smart material based smart actuators. So, like we had discussed about the bimorph, shape memory alloy bimorph. So, we had also discussed about the piezoelectric based bimorph. So, in the case of piezoelectric or a shape memory alloy bimorph, so we had discussed that like the degradation of these actuators basically depends upon the continuous actuation as well as the continuous overloading of these residual stress. So, this effect of residual stress has an impact on the overall life cycle of the actuator. That is like in fact, we had also performed certain amount of experiments with shape memory alloy springs. So, what we have done is, so we have just used the shape memory alloy spring, and those shape memory alloy springs are connected with two hooks, and by using a programmed power supply. So, we are trying to supply a joule heating to it and in a programmed fashion, and a load is tied to this particular spring. So, the spring will expand because of the load, and when we try to supply a heat to it, it comes back to its stage. So, continuous like loading and unloading of this shape memory alloy spring, what will happen is in due course of time, since there is a kind of a thermal heat which exhibits over here, and these thermal heat will try to impact a kind of a actuation in this particular system. So, it will try to attract more amount of these oxide formations on the layers, thus leading to a kind of like until a particular time. So, when these springs are getting actuated, it will try to break the film. However, in due course of time, what happens is these oxide formation will start getting percolated into these lattice of these shape memory alloy structures, which will result in breakage of these, which will result in a kind of a defect formation, and slowly when we try to see the actuation behavior slowly comes down. Now, in this particular case is concerned, since we are considering a spring, so the impact of the residual stress is very limited. However, when we are talking about the bimorph, so we have a kind of a, if we are talking about shape memory alloy based bimorph, so we have a kept-on polyamide. So, this kept-on polyamide is stretched during the deposition, so it is already strained, and that is the reason if you see in the earlier case, we could see a kind of curl kind of structure which was observed in the as manufactured condition, and when we try to supply a heat to it, it became straight. So, that is in the original condition it is like this, and in the actuated condition it becomes straight. So, this is something like switching between the austenite phase and the martensite phase. Now, if we closely observe in this, so in this particular case also, we are trying to use these shape memory alloys for a kind of high frequency actuations, like ideally in the case of micro robotic system. So, we try to deploy it for a kind of a stick slip motions, or we have also seen one kind of peristaltic motions. A similar peristaltic motions can be evolved with such kind of micro robotic based system. So, that like there is going to be a continuous actuation and deactuation which tries to get employed within a short displacement, so that it has a kind of a restriction towards a particular frequency. Okay. Now, in this particular case, so since we are already straining the kept-on polyamide, so there is a chance of a kind of a residual stress which gets imparted into it. Now, when we try to heat it and cool it, that is when we try to actuate and deactuate for a larger life cycles, slowly these residual stress will start getting built up, and finally it will end up in a kind of a failure. So, this is what we had discussed in the last class. Now, as far as in this residual stress is concerned, so like if the effect of residual stress along the, when we try to look into the effect of residual stress along the beam, so like let us consider, when you try to consider a fixed free beam simply expands and contracts, and both the side fixed beam with no bottom constraint holds the stress within this. And similarly, when you try to see over here, a fixed free beam is adhering to the substrate at the bottom. So, these residual stresses in micromechanical system may arise due to the following reason. One is, as I had mentioned earlier, basically it is due to kind of a thin film deposition. In certain cases, it might be due to a thermal expansion of the material. In particular case, in our case, it's a kind of a heterogeneous material. So, of course, there will be a varying thermal expansion which exhibits over here. Then oxidation, substitutional doping or ion implantation during the microfabrication will also participate in having a certain amount of residual stress or imparting a residual stress on the material. Most important aspect is the lattice mismatch in epitaxial growth. In fact, that is the reason in our shape memory alloy Bimorph fabrication, we are ensuring that the Kapton polyamide what we are using has a good match with reference to the shape memory alloy, so that the lattice mismatch is completely eliminated and we have a proper epitaxial growth. In case if there is no proper epitaxial growth is there, it may result in a kind of a poor adhesion, and in due course of time during our life cycle, this shape memory alloys thin film may peel off from the substrate. Next, like as far as in this particular case is concerned, there is a shear force which acts at the right face of the beam in the case of this particular C. So, which is also one of the key point which we may need to consider. Now, when we try to talk about the overall, when we try to look into the overall micromechanics behavior, so let us consider the bending moment arising. So, that is in the earlier SMA Bimorph also we have seen. So, there is a kind of curled structure which is occurring. This is a kind of a bending moment which is arising due to the residual stress or the stress which has been incorporated over here. So, to quantify this residual stress, it is represented as minus m, which is equal to E into I d squared del by dx squared. On differentiating this with reference to dm by dx equals V is the vertical shear force, and again differentiating we get dV by dx equals minus q, which is the transverse load per unit length of the beam. The horizontal component of the forces cancel out while the vertical component add up. Let us consider QR be the transverse load. Now, the transverse load can be represented as theta by phi QR cos theta r d theta, that equals 2 QR r sin phi. So, 2 theta r sin phi bt equals 2 QR r sin phi, and QR equals bt sigma r, bt theta r by r, which is nothing but bt theta r d squared del by dx squared. So, while returning to the original position, there is an additional stress is generated, that is equivalent to the longitudinal stress. Thus, EI d power 4 del by dx4 equals q minus qr, where q equals EI d power 4 del by dx power 4 plus bt sigma r d squared a by dx squared. So, this is the kind of the force like of a transferred load which get generated where because of the bending moment which is arising due to the residual stress which is being incorporated into the system. Now, let us see about the Poisson effect like in the case of a kind of a structure. So, this Poisson effect, we all are aware about this Poisson effect. It is a kind of ratio of lateral strain to a longitudinal strain. Here the bar is, let us consider a bar of length L. So, the bar is longitudinally strained in x direction. The strain is in perpendicular direction is given x, epsilon y equals minus mu epsilon x and epsilon z equals minus mu epsilon x. So, the new length of the bar is given as L dash of x Lx 1 plus epsilon x and then Ly dash equals Ly 1 minus mu epsilon x and Lz dash equals Lz minus 1 minus mu epsilon x. So, the volumetric strain is given as del B by V equals 1 minus 2 mu epsilon x. So, this Poisson ratio has play a vital role. Like currently we are talking about different types of foams which are being efficiently used for like gripping application in microrobots. In certain cases these kinds of foams are used for kind of like which is used for manipulating inside a tubes, and in some cases these kinds of foams are used for a kind of a vibration arresters or a vibration holders for a system. Now, as far as in this Poisson effect is concerned, so I would like to introduce you to this auxetic structure. So, these auxetic structures are a kind of a smart material which has a potential application towards microrobotic related domains. So, if we closely observe these auxetic structures, or we call it as an auxetic foam, these auxetic foam has a capability to have a negative Poisson ratio. Now, what do you mean by this negative Poisson ratio? That is, in the case of a normal foam, so as shown over here in this particular figure, so when I try to pull it in this particular direction, so it is expected that the diameter will get reduced, that is along the breadth it gets reduced, and appropriately it will be compensating along the length. This is a kind of a simple Poisson ratio. However, in the case of auxetic foam is concerned, when we try to pull it, so the structure will also get expanded, that is along the breadth there will be an expansion which is observed. This concept is called as a negative Poisson ratio. So, when we try to look into the overall aspect of this kind of behavior was this kind of structures were well investigated in the year 2012. In fact, in 2012 the first paper on auxetic structures were reported. Later there are many researchers who work on this auxetic structure. So, they also work on 3D printing of these auxetic structures and the usage of these auxetic structures for different applications. So, since these kind of auxetic foam has a potential applications, has a negative Poisson ratio, so it has a potential application in the case of a biomedical. For instance, if there is a wall blockage, these kind of auxetic foam based structures can be integrated, and then when we try to apply a kind of a elongation in this particular orientation, so automatically there will be an expansion in this direction. This expansion will somehow support the removal of the blockage. So, this is one advantage of this system. In addition to this, such kind of auxetic foams can be efficiently used for vibration damping. Okay, so that is like you can also use it as a kind of a vibration arrestor, so that since there is an elongation is happening along the width or along the diameter, so it has a potential application towards arresting the vibrations. So, this is one advantage of this auxetic foam for a negative Poisson ratio. Let us also look into some of the generic aspects related to micromechanics of a torsion of a beam. So, let us consider a simple circular beam. So, this is a kind of a simple fundamental which will give you an exposure to the micromechanic effects in different beams. So, like let us take a simple circular beam. So, in this circular beam, so let us consider the length of the circular beam as L, and the twisting is happening at an angle theta, and R is the radius. So, the beam of length L and R is the radius is subjected to a torque T, and the modulus of rigidity of the bar is represented as G equals E by 2 by 1 plus mu. And the beam rotate by an angle theta. The shear stress generated is given by tau equals G theta R by L, which is nothing but TRJ. So, J is the polar moment of inertia of the beam, and which is useful in torsional spring and the spiral shaped actuators which we had seen earlier. Now, when we try to look into the dynamics of the system, so as far as in order to understand the dynamics of the system, so we should be well versed about the usage of this spring, mass and a damper system. So, like in the case of in order to understand any kind of dynamics, it is always better to consider a spring, mass and a damper system. So, in this particular case, so this is a kind of a spring which is represented by the spring constant, M is the mass and B is the dashpot, which is nothing but a damper which is available. And then when we try to see a kind of a force, or when we try to study the force acting on it, the force F of t is represented as m d square x by dt square plus b dx by dt plus kx. K is the spring constant and b is the damping coefficient. So, the k is introduced and the b is introduced over here, and x is along the plane, and f of t is the kind of force which is exerted. So, when we try to represent this in the form of a free body diagram, so this is a kind of a free body where the force is exerted in this particular direction. There is a kx, and then there is a mass m d squared x by dt square and b dx by dt. So, this is a kind of a spring mass damper model which is being established. Next, one more important aspect with respect to this overall component or the overall characteristics, which we call it as a Coriolis component. So, as far as in this the one of the main example of this Coriolis component is a Foucault pendulum. So, this is a overall schematic of a Foucault pendulum, that is the support of the pendulum rotates about the z axis. So, the ball is oscillating along the y axis and experiences a Coriolis acceleration along the x axis. Now, in this case, let us consider v is the velocity of the ball with the moving frame, omega is the angular velocity of the moving frame relative to the fixed freedom, and the Coriolis acceleration is given by AC equals 2v omega. So, the Coriolis component is applicable in mechanism such as micro machine tuning forks as well as a dual mass vibration gyroscopes. So, these are some of the application of this Foucault this one. So, overall Coriolis acceleration is given as AC equals 2v omega, which is represented over here appropriately.